Okay, so let's unpack this. On April 28th, 2025, at exactly 12:33 in the afternoon, Central European summertime, the electrical grid of the Iberian Peninsula basically just hit a brick wall.
Yeah, you really did.
I mean, in a span of just 3 seconds, the
Yeah.
power systems of Spain and Portugal experienced the most severe, unprecedented blackout Europe had seen in well over 2 decades. Tens of millions of people lost power.
Right, and it's important to note why.
Exactly, because it wasn't a massive hurricane taking down a transmission tower,
Right.
and it wasn't a state-sponsored cyber attack paralyzing some control room somewhere.
No, it was actually far more insidious than that. The lights went out because the fundamental physics of the modern grid just broke down. The system essentially tore itself apart from the inside out.
And that is exactly why we're here today. We are taking a deep dive into an event that fundamentally shook the European energy landscape. And we're doing it with a very specific listener in mind. If you are a policymaker listening to this right now, your decisions, your regulations, the very laws you draft in the coming months, they dictate the resilience of the grid of the future. So our mission today is to help you understand not just the fact that the grid failed, but, the really intricate cascading engineering reasons why it failed.
Because as a policymaker, you are basically standing at the edge of this massive transition. I mean, this blackout wasn't a traditional failure. It was a symptom of a grid caught between two entirely different eras.
Two eras,
We're moving from a system dominated by massive spinning metal turbines, so the traditional power plants we've relied on for a century, to a system powered by inverter-based resources.
Right, wind and solar.
Exactly, which are fundamentally driven by software. And the event on April 28th was this incredibly complex, catastrophic failure of voltage control, reactive power, and automated protection systems that, well, they just completely failed to bridge the gap between those two eras.
Right. So to understand how to regulate this new era, you need to understand the physics of the failure. And we're going to be your guides through the official final report on the grid incident in Spain and Portugal.
Which is quite a document.
Oh, it is. It was published by the ICS Investigation Expert Panel on March 20th, 2026. And it's basically this dense, highly technical autopsy of those terrifying few seconds and really the hours leading up to them.
Yeah, it's honestly a masterclass in forensic electrical engineering. I mean, the panel dissected gigabytes of high-frequency data from across the continent to paint a picture of a system that was essentially suffering from a hidden fatal condition long before the final collapse.
I want to start with the sheer speed of this event, actually, because I think that's the most jarring part for anyone who, sits outside of a control room.
Oh, absolutely. The speed is terrifying.
Okay. We tend to think of infrastructure failures as things we can watch happen and react to, right? Like a bridge slowly cracks, a pipe slowly leaks. But let's look at the timeline of the final cascade here, starting at 12.32.00. This is really the anatomy of a collapse.
Okay, so at exactly 12.32.00, the system voltage in the region begins to rise, and it rises rapidly.
Right.
The report notes that this initial rise was driven in part by the progressive disconnection of about 525 megawatts of wind, solar, and what they call net load down in the distribution grids.
Wait, let's pause there for a second. Define net load for us in this specific context. Like, why does 525 megawatts of that slipping offline even matter?
Sure. So net load is essentially the total electricity demand of the consumers minus the electricity being generated locally right behind the meter.
So think of all the rooftop solar panels on homes and businesses.
Exactly. On a sunny day in Spain, those rooftop panels are pumping out a lot of power, which masks the true demand. So when the panel says 525 megawatts of this mixture disconnected, it means local distribution circuits were literally tripping off.
Oh, wow. Okay.
Yeah, and this instantly changes the delicate balance of the wider transmission grid because it removes both power injection and power consumption simultaneously. It creates this huge ripple effect.
So the system is suddenly dealing with this unexpected ripple. The voltage is creeping up. And then, just 57 seconds later, at 12.32.57, a really critical domino falls. A power transformer trips at a specific substation, the 400 kilovolt TS1 Granada substation.
And that single trip is where the situation upgrades from, a concern to a localized crisis. Because that transformer dumping offline takes 355 megawatts of renewable generation with it.
Right.
But much more crucially for our story, it cuts off 165 megavars of reactive power absorption.
Okay, let's plant a flag in that term right there, reactive power absorption. We are definitely going to spend a lot of time on reactive power today. But for right now, the listener just needs to know that losing that absorption was, well, it was basically like taking the brakes off a speeding car heading downhill.
A very heavy car. Because without those brakes, the voltage isn't just creeping up anymore, it is skyrocketing.
Yeah.
Between 12.33.18 and 12.33.21, the voltage across southern Spain spikes violently, and this massive overvoltage triggers a widespread panic among the remaining generation facilities.
Because they're trying to protect themselves.
Exactly. Solar panels and wind turbines, sensing the dangerous voltage, they just start tripping offline en masse to protect their own internal circuitry.
And when they trip, they take even more of those breaks, like their own passive reactive power absorption with them.
Yeah.
So it just feeds the monster. The voltage spike gets even worse, which causes even more plants to trip. It is a literal death spiral happening in the blink of an eye.
It really is. I mean, by 12.33.1 R9, so just 19 seconds after the Granada substation trip, the situation fundamentally shifts. Spain and Portugal literally start losing synchronism with the rest of Europe.
Losing synchronism. That implies they were previously moving together. You're talking about the 50 hertz electrical frequency, right?
Yes. So the entire continental European grid operates as one massive synchronized machine humming at exactly 50 hertz. Every major generator from Portugal to Poland is magnetically locked into that same rhythm.
It's incredible when you think about it.
It really is. It held together by what engineers call synchronizing torque. But when the voltage collapsed in Spain due to those massive plant trips, the magnetic glue holding the Iberian generators to the French generators basically dissolved. The synchronizing torque plummeted.
Okay, I'm picturing a massive, perfectly choreographed, synchronized swimming routine. You've got thousands of swimmers, which are our power plants, all moving to the exact same 50 hertz rhythm, holding hands.
Okay, yeah.
And if one swimmer suddenly kicks too high, which is our localized voltage spike, they break their hold and knock into the swimmers next to them.
That's really helpful visualization, actually. The disturbance is totally physical and immediate.
So the collision spreads through the water. At 12.33.20, the AC interconnection to Morocco trips offline. The swimmers at the edge of the pool are out. And then at 12.33.21, the automated relays at the French border detect the absolute chaos, and they just sever the ties to France. They have to protect the wider European grid from being dragged down into the dark. So within 3 seconds of the major spike, the entire Iberian pool is drowning.
Yeah. The forensic data shows the rate of change of frequency, or ROCOF, exceeded 1 hertz per second in that exact moment.
Wow.
And that metric might sound small to an outsider, but in power systems engineering, a 1 hertz per second plunge is catastrophic. It is literally the electrical equivalent of driving into a concrete wall at highway speeds.
And this brings us to the first really stark reality for the policymaker navigating this transition. As a lawmaker, you deal in deliberate timelines, right? Committees, hearings, drafts, votes. But the system you are regulating reaches the point of no return in 3 seconds.
Yeah, human reaction time is completely, utterly irrelevant here.
Exactly. You cannot have a highly trained operator sitting in a control room in Madrid, waiting for an alarm to pop up on a screen, taking a sip of coffee, assessing the data, and clicking a mouse to save the grid.
No, the human brain simply cannot process the influx of data, formulate a plan, and execute it before the synchronizing torque just evaporates.
So if the system's defenses aren't fully automated and perfectly tuned by engineers beforehand, and legally mandated by you, the policymaker, to operate dynamically without human permission, the grid is lost before the operator even blinks.
Which is a terrifying thought, but it really emphasizes why policy must focus on preemptive, automated resilience. Because while the final death spiral took 3 seconds, the blackout didn't actually come out of nowhere.
Right, there were warning signs.
Exactly. The grid was giving off signals. It was, for lack of a better term, shivering in the half hour leading up to the collapse.
This is where the detective work in the ICS report gets truly fascinating. The timeline shows that between 12:00 and 12:30, the Iberian Peninsula was affected by 2 very prominent oscillatory phenomena. The grid started swinging.
Yeah, and an oscillation in a power grid is essentially a periodic, rhythmic fluctuation of electrical quantities. You can see the voltage, the frequency, and the flow of power swinging back and forth, almost like a pendulum.
So the first wobble happened between 12.03 and 12.08. It was a 0.663 hertz oscillation. And the report mentions that the expert panel used something called eigenvalue analysis to figure out what caused it.
Right.
What does that actually tell the investigators, in plain English?
So eigenvalue analysis is a mathematical technique used to find the hidden natural frequencies where a complex system naturally wants to vibrate.
Okay.
Think of a suspension bridge. It has a natural resonant frequency. If the wind hits it just right, it starts to wobble. The grid is the exact same way. The investigators used this math to look at the grid's topology and basically asked, was this 0.63 hertz wobble a natural inherent flaw in how the lines are connected?
And what did they find? Was it natural?
They found that it wasn't natural at all. It was a forced oscillation. Something was actively pushing the pendulum.
Pushing it.
Yeah, the report explicitly links this to converter-driven instability interacting with other generators in that specific area of the grid.
Okay, converter-driven instability. That sounds like the smoking gun for the energy transition. Is this fundamentally a side effect of moving away from those massive spinning metal turbines that have physical inertia and relying more on the software-driven inverters that connect our solar and wind farms to the grid?
It is entirely a product of the modern grid architecture. Traditional generators like coal, nuclear, hydro-D, they naturally dampen these kinds of swings because of their immense physical mass.
Right, because they're huge.
Exactly. A multi-ton steel rotor spinning at 3,000 RPM does not want to change speed easily. It just absorbs the wobbles. But inverter-based resources, or IBRs, they don't have that physical mass. They use complex power electronics and, well, millions of lines of software code in their control loops to interact with the grid.
So they are constantly reading the grid's voltage and frequency and using algorithms to decide how much power to inject?
Correct. But if those control loops aren't perfectly tuned, or if they are operating in a physically weak part of the grid where the voltage is already a bit unstable, the software can overcorrect.
Oh, I see.
It reads a slight dip, injects power to fix it, overshoots, reads a high voltage, pulls back, overshoots again. The software control loops actually start fighting themselves, and they inject oscillating energy into the system. They force the grid to swing.
That's a brilliant breakdown. So the modern equipment essentially created its own earthquake. And while that 0.63 hertz swing was relatively localized, it wasn't the only one.
No, it wasn't.
Between 12.19 and 12.22, a second oscillation emerged, a 0.2 hertz swing. And this one was classified as an inter-area oscillation affecting the entire east-center-west continental grid.
Yeah, a much wider, slower swing.
Yeah.
The entire European continent was feeling this pendulum. The report actually analyzed the France-Spain high-voltage direct current link, the INLFE1, to see if it could have dampened the swings. But the core finding was a glaring absence of internal damping within the Iberian system itself. Many large, traditional power plants lacked functioning power system stabilizers, or PSS, and the ones that had them just weren't acting aggressively enough to flatten the curve.
So as a policymaker listening, you might be thinking, okay, the grid shivered for a bit, but it didn't collapse during those swings. Why are we spending so much time on the pregame jitters?
Well, we have to focus on the pregame because of how the human operators were forced to respond to those exact jitters. Those early oscillations caused localized low-voltage events. The pendulum swung low.
Right.
So to prop the voltage back up and keep the grid stable, grid operators in Spain had to take manual action. They reached out and disconnected several major shunt reactors.
Ah, okay. I promised we'd get back to this. A shunt reactor. Walk us through exactly what this piece of equipment is and the physical role it plays, because this decision basically seals the fate of the grid 25 minutes later.
Right. So a shunt reactor is a massive, incredibly heavy piece of electrical equipment that sits at a substation. It looks somewhat like a transformer, and its entire job is to absorb reactive power.
We're going to need to dig deeply into reactive power in just a moment, but let's stick to the high-level effect first.
At a high level, absorbing reactive power lowers the voltage of the transmission line. It basically acts as an anchor. So when the operators were facing those low-voltage swings caused by the oscillations, they needed to release the anchors to let the voltage float back up to safe levels, so they manually switched the shunt reactors off.
Which, I mean, that makes total sense in the moment. You're trying to fix the immediate problem in front of you.
Oh, absolutely. It was the logically sound operational choice for a low-voltage crisis. The tragedy is that 25 minutes later, at 12.32, when the Grenada transformer tripped and the massive high-voltage spike hit, those shunt reactors were physically disconnected from the grid.
And they couldn't just turn them back on.
No. Because they are mechanical devices operated by human command, there was absolutely no time to process the new, terrifying overvoltage crisis, make a decision, and mechanically reconnect them before the system collapsed.
They took down their shields to survive a small skirmish, and their shields were still sitting on the ground when the main cannon fired.
That is exactly what happened. The grid was left entirely defenseless against a high-voltage surge.
As a policymaker, you are looking for the action item here. You can't just cross your fingers and hope the software of the solar inverters plays nice with the grid, and you definitely can't rely on operators manually clicking switches to deploy shields in a 3-second window.
Exactly. You have to regulate the automation. You need stricter testing and certification for all inverter-based resources. Grid codes must explicitly require mandatory tested oscillation damping capabilities from these software-driven plants.
You have to prove you can help.
Right. You cannot allow a plant to connect to the grid merely to sell energy. You must force them by law to actively prove they can stabilize the grid they are profiting from. Furthermore, you must ensure traditional plants have fully functional power system stabilizers active at all times.
That sets us up perfectly for the main event. The grid drops its guard during the oscillations. Then, at 12.32, the sudden voltage spike hits. Why couldn't the system handle it? Why was it so fatal?
Yeah.
This brings us to the absolute core technical failure of the whole event, and arguably the most important engineering concept a policymaker needs to grasp regarding the modern grid reactive power.
If you take only one technical concept away from this deep dive to bring back to your legislative committees, make it reactive power. It is the invisible scaffolding of the electricity system.
Let's try to break this down because it is notoriously difficult to explain without drawing phasor diagrams on a whiteboard.
It is, yeah.
Let's talk about the difference between active power and reactive power.
Okay, let's start with active power, which is sometimes called real power. This is the stuff that does the actual work. It spins your blender, it lights your LED bulbs, it charges your electric vehicle. It is measured in watts or megawatts. When you pay your electricity bill, you are paying for active power.
Okay, so if active power is doing all the work, what is reactive power doing?
So in an alternating current or AC grid, the current is constantly reversing direction 50 times a second. To push that current across hundreds of miles of transmission lines, you need a magnetic field. Reactive power, which is measured in VARs or megavars, is the energy that constantly flows back and forth between generators and the grid to build and maintain those magnetic fields.
Right.
It doesn't do work for the consumer, but it maintains the voltage levels that allow active power to flow at all.
I want to try an analogy here. Tell me if this holds up. Think of active power as the engine pushing a car forward down the highway. But reactive power is the tire pressure and the suspension system keeping the car on the road. Without the suspension, the car shakes itself to pieces, the wheels lift off the pavement, and forward motion becomes impossible.
I really like that. Let's build on the suspension idea, specifically the shock absorbers.
Okay.
If you're driving on a perfectly flat road, your shock absorbers are just holding the car level. But the moment you hit a massive pothole, like a generator suddenly dropping offline,
Right.
you need those shock absorbers to dynamically compress and expand instantly to keep the chassis level. Electrically, reactive power dynamically absorbs or injects energy to keep the voltage level steady when the grid hits a pothole.
Okay, so to lower spiking voltage, which is the crisis Spain faced at 12.32, the system must absorb reactive power. The shock absorbers need to compress.
Exactly.
Let's look at the shock absorbers Spain had available on April 28th, starting with the shunt reactors we just talked about.
Right. Out of 7,700 megavars of shunt reactor capacity across Spain, 42% was disconnected right before the blackout.
And in southern Spain, where the crisis originated at the Granada substation, it was far worse.
Much worse. 67.5% of the shunt reactors in southern Spain were disconnected. The manual shock absorbers were simply missing from the car.
That's strike one. The dedicated voltage control equipment was sidelined. But what about the traditional power plants? I mean, a coal plant or a radiator plant doesn't just produce active power. Their massive spinning alternators can generate or absorb reactive power too, right?
They absolutely can, and they are legally required to do so. Grid operators send them a Q reference, which is a dynamic reactive power target they're supposed to hit to support the grid.
Okay.
But the forensic data from the report exposed a severe conventional generator failure. The data showed that these traditional plants reached their mandated Q reference in less than 75% of the hourly samples leading up to the event.
Wait, less than 75%. So they were legally supposed to provide a certain amount of support. They were instructed to do so, and they simply failed to perform.
Yes.
That's strike two. The traditional plants are severely underperforming. But Spain has undergone a massive energy transition. What about all the new renewable energy, the massive solar parks and wind farms? Surely they could step up and provide this reactive power support.
This is where we uncover the critical failure of the entire event, and perhaps the most urgent lesson for any policymaker regulating the future grid. The vast majority of renewable energy sources, or RES, were permitted to operate at what is called a fixed power factor.
A fixed power factor. What does that actually mean in practice for the grid?
It means their shock absorbers were effectively welded shut.
Welded shut. Wow.
Yeah. A fixed power factor means the solar or wind plant is programmed to just pump out active power, maximizing its revenue, while maintaining a static, unchanging ratio of reactive power. They are completely blind to the grid's actual needs.
Oh, no.
So when the voltage started spiking violently, they did absolutely nothing to dynamically react. They did not increase their reactive power absorption to help compress the shock absorber.
Why would they be programmed that way? Is the technology just not capable of it?
Oh, the technology is more than capable.
Yeah.
Modern smart inverters can adjust their reactive power output in milliseconds, which is far faster than a physical spinning turbine.
So why not do it?
The reason they were set to a fixed power factor is purely a legacy regulatory issue. Historically, renewables were small. They were treated as grid followers. You didn't want a small rooftop solar array trying to dictate voltage. But now, renewables are the dominant force on the grid, yet they are still operating under rules designed for minor players.
So they did nothing to help. But as we discussed earlier, it's actually worse than doing nothing, isn't it?
Much worse, because as the voltage spiked higher and higher, the internal protection sensors inside these fixed power factor solar plants triggered. The plants tripped offline to protect their own hardware from melting. And when they tripped, two things happened simultaneously. First, we lost their active power, causing a sudden deficit in energy supply. But second, and more fatally, the grid also lost whatever baseline static reactive power absorption they were passively providing.
It's just an agonizing compounding effect. You lose the active power, which destabilizes the frequency. But losing their passive reactive power absorption causes the voltage to spike even further.
Yes, which causes another solar plant 5 miles down the road to experience an even higher overvoltage, triggering its protection relays. It trips, which causes an even higher spike. The car hits a pothole, the shock absorbers are either missing or welded shut, the chassis violently bounces, and the whole vehicle flips over.
And the report's technical analysis is unambiguous here, right? Increased reactive power margins could have prevented the system collapse. The physics could have been managed.
The physics were entirely manageable. What failed was the regulatory framework managing the physics.
As a policymaker, you are staring at a systemic regulatory failure across all generation types.
Absolutely. I mean, think about the conventional generators. The framework lacked strict dynamic behavior criteria, and crucially, there were no economic penalties for non-compliance.
Right.
If a traditional gas plant didn't meet its Q reference to support the grid, there were no teeth in the regulations to punish them. They prioritized active power sales over grid stability because stability wasn't economically enforced.
And on the renewable side?
On the renewable side, it's even more frustrating. The report notes that Spain actually had a pilot program running that allowed some renewables to perform real-time dynamic voltage control. They proved the smart inverters could successfully stabilize the grid, but it was an optional experiment. The policymaker takeaway here is simple but profound. Dynamic reactive power provision must be the absolute mandatory default for all generation connecting to the grid, not an optional add-on. You have to force the shock absorbers to be unlocked by law.
We have to mandate resilience. Okay, let's move into the next phase of the collapse. The voltage is spiraling out of control. The cascade of tripping solar plants has begun. This is the moment when the grid's automated protection systems, so the relays, the circuit breakers, the last lines of defense are supposed to kick in, isolate the problem, and save the wider system.
That is their sole purpose. Protection systems are designed to detect abnormal conditions, limit damage to expensive equipment, and prevent the propagation of faults.
Okay.
But the investigation uncovered a deeply disturbing reality. In this scenario, instead of saving the grid, poorly configured protection systems essentially poured gasoline on the fire.
You're saying the safety nets actively destroyed the system? How is that even possible?
It comes down to misaligned overvoltage settings. The expert panel pored over the data logs of hundreds of disconnected plants and found that many generation facilities, especially those solar PV plants, had protection settings configured deep inside their inverters that completely diverged from legal requirements.
Diverge. Are you saying they were actively breaking the law?
Let me give you a highly specific example from the forensic data. There is a legal requirement category in the European grid codes called a V3 module. Under this rule, a generation facility is legally required to withstand a high-voltage event, specifically a spike up to 440 kilovolts for up to 60 minutes without disconnecting.
Okay.
It is mandated to ride through the storm to provide whatever stability it can.
Okay. 60 minutes at 440 kilovolts, that is the legal baseline for survival. What did the actual data show?
The report found one PV plant that tripped offline at an overvoltage setting of just 435.6 kilovolts, and it did so after a delay of only 1.5 seconds.
Wow.
Another plant tripped at 440 kilovolts after the threshold was exceeded by a mere 0.6%, and it tripped in less than a single second.
Wait, let me process that. The law clearly states you must stay online and help the grid survive this high voltage for 60 minutes. And the solar panels essentially panicked, ignored the 60-minute rule, and shut themselves off to protect their own hardware after 1 second.
Yes, they acted in pure self-preservation. From the perspective of the individual solar plant owner, tripping offline saves their expensive inverters from potential long-term degradation.
Sure, saves them money.
But from the perspective of the transmission grid operator, that premature tripping actively destroyed the larger system by accelerating the reactive power deficit. The expert panel explicitly notes that at least 10 major plant disconnections during those 3 seconds were definitively not in line with applicable legal requirements.
That has to be infuriating for the grid operators trying to manage the collapse. Why would plant owners configure their settings so aggressively? Is it just malicious compliance to save money?
It's rarely malicious. It's often a combination of risk aversion and a fundamental quirk in how the Spanish transmission grid was designed decades ago.
Oh.
The Spanish 400 kilovolt grid operates at a wider normal voltage range than most of the rest of the European Union. They routinely run their lines up to 435 kilovolts under normal daily operations.
So they run their grid hot, so to speak. Why do that?
Pushing voltage higher reduces the amount of current needed to deliver the same amount of power, which reduces the heat lost in the wires over long distances. It's really efficient.
Makes sense.
But here is the massive flaw. While they operate normally at 435 kilovolts, the hard emergency trip thresholds for the equipment connected to it are still legally around 440 kilovolts.
Ah, I see the trap.
The trap is the margin. When the Spanish grid is running normally but on the high end of its curve, there's almost zero safety margin before it hits the panic threshold of the connected equipment. You have a 5 kilovolt buffer on a 400 kilovolt system.
That's nothing.
It's a razor-thin margin for error. The slightest hiccup, like a single transformer tripping in Granada, pushes the system over the cliff instantly.
It's like driving a car where the speed limit is 85 miles an hour, but the engine is programmed to violently shut off if you hit 86 miles an hour. You have no room to maneuver.
Exactly.
And it wasn't just the solar plants that had relay issues, right? The report extensively covers something called Distance Protection Zone 1 trips. What are those, and how did they fail?
Distance protection relays are the guardians of the massive high-voltage transmission lines. They are designed to detect internal physical faults on a specific stretch of wire. For instance, if a tree falls and shorts out the line, or a lightning strike causes a flashover to the ground.
Okay.
They calculate the electrical distance to the fault by measuring voltage and current, and if they detect a physical short circuit, they instantly pop the circuit breakers to isolate that line.
But there weren't any trees falling during this event.
Exactly. There are no physical faults at all. But remember the chaos of those final 3 seconds. The voltage was violently collapsing in some areas and spiking in others. The frequency was tearing apart, and huge, chaotic swings of current were sloshing back and forth across the peninsula as the synchronizing torque failed.
Just total electrical chaos.
Right. And the distance relays at several key substations basically got overwhelmed by the math. They misread this chaotic system-wide voltage collapse as a physical short-circuit fault on their specific line. They hallucinated a fallen tree, and they tripped the healthy lines open.
They panicked because the data looked like a localized physical break, when in reality it was a macroscopic system failure.
Precisely. Now, it's vital to contrast those hallucinating relays with the relays at the French border. Those are called loss of synchronism relays. Their explicit job is to watch for the macroscopic system failing.
So they did their job.
Beautifully. When Spain started tearing away from the 50 Hz European frequency at 13.33.21, those French border relays detected the severe out-of-step swinging accurately. They watched the voltage swing once, twice, and on the second swing, they operated flawlessly, severing the interconnections and saving the rest of the European continent from being dragged into the blackout.
So we have a situation where some relays acted as heroes, doing exactly what they were designed for, while others panicked and exacerbated the collapse, or were actively configured illegally to save themselves. As a policymaker, you hear this and a giant red flag goes up. If these solar plants had illegal protection settings, why didn't the grid operator know about it beforehand? Why wasn't it caught?
You've hit on the most glaring administrative blind spot highlighted in the entire report. It comes down to poor visibility at the TSO-DSO boundary.
Let's define those acronyms for everyone. TSO is the transmission system operator, and DSO is the distribution system operator.
Yes, the TSO manages the massive, high-voltage inner-city highways. The DSO manages the low-voltage local roads running through your neighborhood. Historically, power only flowed one way, from huge generators on the highways down to the local roads.
Right.
The TSO didn't need to know much about the local roads. But today, millions of solar panels are connected down on those local roads, pushing power back up. The transmission operators simply do not have the data streams to see the specific relay settings deep inside those distribution-level solar plants.
So the people responsible for keeping the entire country's grid stable are essentially flying blind regarding how a massive percentage of their generation will behave in a crisis.
Yeah. They didn't know the plants were going to illegally trip until they watched the megawatt dials plummet to zero on their screens.
That is deeply unsettling. So what is the legislative fix here? How do you legislate transparency?
With strict enforcement mandates, you must mandate cross-TSO-DSO data sharing. The transmission operator needs legal authority to demand real-time telemetry and configuration data from distribution-connected generation. They need to know exactly how those plants will behave in a voltage crisis.
Right.
Furthermore, you have to force plant owners to regularly inspect, certify, and prove their relay settings match the legal grid codes.
It's exactly like fire codes for a commercial building. You don't just write the fire code and hope the building owner buys the right sprinklers. You send a fire marshal to physically inspect the sprinkler system, you demand a certificate of compliance, and you levy massive fines if the system is disabled.
That is the perfect analogy. You cannot operate a highly volatile modern grid on the honor system. The risks are simply too high.
Okay, we are moving into the aftermath. The cascade has finished. The grid has collapsed. The automated defenses failed or hallucinated. The Iberian Peninsula goes dark. Let's talk about the system defense plan and the dark reality of trying to wake a dead grid back up.
Yeah. So when the frequency plummeted in those final agonizing seconds, Spain and Portugal's ultimate last resort safety net activated. This is the system defense plan, specifically an automated protocol called the Low Frequency Demand Disconnection Scheme, or LFDD.
I've heard of this. This is essentially controlled rolling blackouts, right? Shedding consumer load to save the wider system from a total blackout.
Correct. The fundamental rule of grid physics is that supply must perfectly match demand at every given second. If a massive generator trips offline, you suddenly have more demand than supply. The heavy load drags the frequency down below 50 Hz.
So you have to cut load to balance it out.
Exactly. The only way to stop the frequency from crashing is to quickly shed demand to rebalance the scale. The LFDD automatically cuts off large industrial consumers, pump storage hydro plants, and eventually residential feeders. And according to the forensic data, the LFDD relays worked perfectly. They detected the low frequency, and they shed the load they were programmed to shed.
But the grid still collapsed. The patient still died.
Yes. And here we uncover a tragic irony that highlights the growing pains of the energy transition. The LFDD is designed to fight a frequency drop. It is predicated on a traditional grid problem. We lost a big physical power plant, therefore we must cut consumption. It is utterly blind to the modern reality of inverter-based grids where voltage collapse is the true killer.
So what happened when the LFDD shed the load during a voltage crisis?
Remember that the primary crisis was a massive overvoltage. When the LFDD suddenly disconnected massive amounts of load, which included grid users and industrial motors that were actively absorbing reactive power, it removed even more shock absorbers from the system.
Oh, wow.
Furthermore, when you suddenly remove demand from a long transmission line, you trigger something called the Ferranti effect.
The Ferranti effect. Explain that for us.
A long, high-voltage transmission line isn't just a simple wire. It acts as a giant capacitor. It naturally stores electrical charge. When the line is heavily loaded with consumers, that charge is managed. But if you suddenly cut the consumers off, leaving the line lightly loaded or empty, the capacitance of the long line actually generates excess reactive power, which violently pushes the voltage even higher at the receiving end.
Wait, let me make sure I understand this. The system was dying of an overvoltage spike. The defense mechanism saw a frequency drop, panicked, and cut off the consumers. But cutting off the consumers actually caused the lines to generate more voltage, making the primary overvoltage problem exponentially worse.
That is exactly what happened. The defense mechanism acted like a severe autoimmune disease. It did precisely what it was programmed to do by its legacy designers. But because the disease was a modern voltage spike instead of just a traditional generation deficit, the cure inadvertently killed the host.
That is a brutally accurate and terrifying reality. The system defense plan is a relic of a mechanical past trying to govern a digital future. It just has to be modernized.
It really does. But before we get to modernization, we have to look at the restoration process. The system is dead. Millions are in the dark. Now the operators have to wake it back up. The report's analysis of the restoration provides incredible lessons for policymakers.
Walk us through it. How do you restart an entire country's electricity?
There are two primary strategies to restore a dead grid top-down and bottom-up. The report shows Spain used both, with vastly different levels of success.
Let's start with top-down. How does that work?
Top-down restoration is when you rely on a healthy, functioning neighboring grid. In this case, France still had power. Spanish operators slowly reached across the border, carefully re-energizing one transmission line at a time, feeding stable French power into the dead zones of northern Spain.
Sounds logical.
The report notes this top-down approach worked beautifully. The massive French grid provided a massive anchor of stable voltage and frequency, allowing the Spanish grid to slowly rebuild itself piece by piece, synchronizing new generators to the French rhythm.
Okay, that sounds methodical and safe. But what about the places deep in southern Spain or Portugal, hundreds of miles away from the French border? You can't just run a single extension cord that far.
Exactly. For those deep regions, you must rely on bottom-up restoration, which is widely known in the industry as a black start. This is where the true nightmare of operators begins.
Why is it a nightmare?
You have to use specific power plants, usually hydro plants with physical turbines, that have special diesel generators on site. They use the diesel to start their own massive turbines without needing outside grid electricity. Once they are spinning, they slowly try to build an isolated, fragile island of power from scratch, adding one neighborhood at a time.
This sounds incredibly delicate. You're trying to balance supply and demand manually on a tiny scale?
It is arguably the most stressful task an operator can perform. And during this event, the black start process struggled massively. The primary issue, once again, was voltage control.
How so?
In one detailed instance, a hydro plant, the HPP Galicia 2, was successfully black-started and was trying to stabilize a small island grid. But as they tried to energize empty transmission lines, the voltage rose too high. The hydro plant's internal overexcitation protection relay tripped to protect the generator, and the entire island collapsed back into darkness.
Why did they struggle so much to keep the voltage balanced? Was it just the Ferranti effect again?
Partially. But a massive modern variable threw chaos into the process distributed energy resources, or DERs. Think about all the rooftop solar panels and small home battery systems connected to the distribution network. They are programmed to generate power when they sense the grid is alive.
Oh no, I see where this is going.
Yes. When the hydro plant operators would delicately, painstakingly energize a local area to bring on just enough consumer load to balance their generator, these thousands of uncoordinated DERs would sense the voltage returning. Their internal software would think, the grid is back. And they would automatically reconnect themselves, suddenly injecting megawatts of unexpected active power into a fragile, microscopic island grid.
Which completely throws the delicate balancing act out the window.
Exactly. It destabilized the Black Start Islands repeatedly. The human operators are trying to balance a highly sensitive scale using tweezers, and these automated solar panels keep blindly throwing handfuls of sand onto the scale.
So the transition to rooftop solar actually makes recovering from a blackout significantly harder if they aren't controlled. That is a massive hardware and software problem. But the report also highlights a severe human infrastructure failure during the restoration, didn't it? Something regarding communications.
Yes, and this is a critical vulnerability that extends beyond just electricity. When the power grid goes down, the backup batteries on public cell phone towers only last for a few hours. There was a critical loss of voice communication because the public telecommunications networks completely failed in major regions like Galicia, Sevilla, and Madrid.
But wait, how can you restore a grid if the control room operators can't talk to the substations or the power plants to coordinate which switches to throw?
You can't. Or, at best, you have to drive a person in a truck to the substation to physically see what's happening. The telecom failure caused massive cascading delays in load recovery. The operators were essentially deaf and blind while trying to perform the most delicate engineering task imaginable.
So synthesizing all of this for the policymaker listening, what are the hard mandates that need to be drafted to fix the restoration process?
There are three non-negotiable mandates here. First, you must mandate and fund blackout-proof, independent voice and data communications for all critical grid operators, transmission nodes, and major generating stations. They absolutely cannot rely on commercial public cell networks that die when the grid dies.
And second, regarding those thousands of rooftop solar panels throwing sand on the scale.
You must tightly regulate the reconnection protocols of all DERs. By law, they must be programmed with delayed, randomized reconnection timers. When they sense the grid return, they should not all jump on simultaneously. They need to wait 5 minutes, 10 minutes, randomly distributed, so they don't blindly auto-reconnect and crush a black start island.
And the third mandate.
Modernize the system defense plan. The LFDD cannot just look at frequency anymore. It must be legally required to incorporate voltage-based detection logic. It has to be smart enough to recognize a voltage cascade and react appropriately, perhaps by triggering fast reactive power reserves rather than blindly shedding consumer load and making the overvoltage lethally worse.
This brings us to the grand finale of the report and the core of why we are doing this deep dive. We've dissected the timeline, we've diagnosed the patient, we've performed the autopsy on the relays, we've seen the immune response of the defense plan. Now let's talk preventative medicine.
Right.
What exactly does a policymaker need to draft into law tomorrow to ensure April 28, 2025 is the last time Europe goes dark like this?
The final section of the report includes a fascinating visual aid. It's a diagram called the root cause tree. It meticulously maps out the physics of the cascade, tracing every tripped relay and voltage spike back to its origin. But the expert panel did something highly intentional. They colored certain boxes on this tree blue.
Blue boxes.
Yeah. The physical failures are one color, but the blue boxes represent the regulatory, economic, and operational frameworks that allow the physics to run amok.
I really love that framing, because as a legislator, you can't legislate physics, you can't pass a law making electricity travel slower, and you can't repeal Ohm's law. But you absolutely have power over the blue boxes. You regulate the environment in which the physics operates.
Exactly. The report distills its massive technical analysis down to 5 critical, urgent recommendations that directly address those blue boxes. These are the policy levers.
Let's explore them deeply. What is the legislative silver bullet for the fixed power factor renewables that acted like welded shut shock absorbers? Recommendation 1.
Recommendation 1 is mandating dynamic reactive power capability. The era of renewables being passive grid followers must end immediately. You must mandate that all generation, especially the rapidly growing fleet of utility-scale solar and wind, must be capable of dynamic, real-time voltage control.
No more fixed power factor.
You must legally abolish the fixed power factor operational mode for transmission-connected resources. Remember those pilot projects Spain ran that proved the smart inverters could stabilize the grid? Those can no longer be optional experiments. They must become the foundational law of the land for grid interconnection. If you want to sell power, you must provide active stability.
And recommendation 2. How do we deal with the human operators who are too slow to reconnect the shunt reactors?
Recommendation 2 is the automation of voltage control. The TSOs must be mandated to fully automate the switching of their shunt reactors and other static reactive power devices. We saw exactly what happened when human operators had to manually switch them off during the early oscillations. They were left disconnected when the real 3-second crisis hit.
Right.
Human operators are simply too slow to manage converter-driven cascades. You have to remove the human from the millisecond decision loop. Automate the deployment of the shock absorbers.
Recommendation 3 addresses the hallucinating relays and the illegal settings. How do we force plant owners to actually obey the grid codes?
Enforce the grid codes with severe economic consequences. You must introduce TSO-coordinated field inspections. As we discussed, the transmission operators need the legal authority and the budget to physically inspect and audit distribution-level plants.
Right.
If a PV plant's protection settings are misaligned with the law acting in self-preservation instead of grid preservation, like we saw with those V3 category failures, they must face heavy, immediate economic penalties or be forcibly disconnected from the grid until they prove compliance.
Send in the electrical fire marshals and give them the power to shut the building down. Recommendation 4. This addresses the Spanish transmission quirk.
Fix the margin. You must address the operational range quirk of the Spanish 400 kilovolt grid. You cannot sustainably run a system where normal, daily operations sit right on the razor's edge of emergency trip thresholds. The policy must legally mandate a wider buffer zone between high normal voltage and the point where equipment is allowed to panic and shut down. Give the system room to breathe and recover before the dominoes start falling.
And finally, recommendation 5. How do we spot the warning signs earlier?
High-frequency monitoring. Remember that 0.63 Hz forced oscillation that weakened the grid 30 minutes before the crash. That kind of instability can no longer go unnoticed or unaddressed. Policymakers must mandate the installation of high-frequency and power-quality monitoring tools at individual IBR plants and sub-transmission areas. Grid operators need granular, millisecond-level visibility to catch those software-driven oscillations and retune the inverters before they cause system-wide instability.
As a policymaker, you have the hardest job here, and I want to voice a challenge on your behalf. We've spent an hour detailing how complex and fast the system is. By definition, regulation moves at the speed of bureaucracy. It takes months to draft laws, hold committee hearings, debate the economic impacts, and pass mandates.
Yeah.
But this grid reached the point of no return in 3 seconds. How do you regulate something that fails faster than a human can blink? Can policy actually catch up to the technology, or is this just an unwinnable race?
It is a profound challenge. But viewing it as a race mistakes the fundamental role of regulation. Regulation doesn't need to react in 3 seconds. It needs to prepare the system long before those 3 seconds ever arrive.
I see.
The tragedy of the April 28th blackout isn't that we lack the technology to stop it. The hardware to prevent this is smart inverters that can dynamically inject reactive power, the automated relays, the correct software settings. That technology already exists. It was sitting right there in Spain, bolted to the ground.
It just wasn't turned on, or it was configured selfishly.
Exactly. It was the lack of legal and economic mandate that caused the failure. Generators operate on economics. They will not invest in dynamic voltage control, and they will not configure their relays to ride through dangerous storms unless they are economically paid to do so or heavily penalized for failing to do so.
Right.
Regulation is the only tool that forces the technology to behave for the collective good. If you endure the slow bureaucracy to draft the right laws today, you build the automated, resilient physics of tomorrow.
That is an incredibly powerful perspective. Let's take a moment to summarize the massive journey we've been on. We tracked a catastrophic European blackout, not triggered by a storm or an attack, but from a fundamental breakdown within the physics of the grid.
Right.
It started with a slight 0.63 Hz wobble, driven by the software of modern inverters, which forced operators to manually drop their voltage defenses.
The manual shock absorbers vanished.
Then, a single transformer tripped, dumping massive amounts of reactive power absorption. The voltage spiked violently, panicking millions of fixed power factor solar panels into tripping offline to save themselves, which removed even more reactive power and worsened the spike.
The dominoes fell in 3 seconds.
The Automated Defense Plan, the LFDD, acted like an autoimmune disease, blindly shedding load to fix a frequency problem, but accelerating the overvoltage crisis by triggering the Ferranti effect.
Yeah.
Ultimately, the entire Iberian Peninsula tore itself off the European grid, plunging tens of millions into darkness, and the restoration was crippled by reconnecting rooftop solar panels and dying cell phone towers.
It was a cascade of microscopic regulatory failures resulting in macroscopic darkness.
Which leaves us with a chilling concept to mull over. It's heavily implied by the data we've discussed today, but it represents a philosophical shift. As we aggressively decarbonize, we are pulling out those massive, inertia-heavy, spinning metal turbines.
Right.
We are replacing them with millions of decentralized, software-driven solar panels and wind turbines. We aren't just changing the source of our energy to make it cleaner. We are fundamentally, irreversibly changing the speed of the grid.
That is the ultimate takeaway. The European power system is no longer a heavy mechanical beast that moves slowly. It has transitioned into a highly sensitive, hyper-fast digital network.
Right. And as you return to your legislative committees, it forces us all to ask the ultimate question. Are our laws, are our human operators, and are our own bureaucratic minds truly ready to govern an electricity grid that can now collapse at the speed of software?
It is the defining infrastructure challenge of our generation.
And the power to ensure the lights stay on is, quite literally, in the hands of the policymakers listening to this right now. Thank you for joining us on this deep dive. We'll see you next time.